Hi everyone, this is Dr. Bezat Mohammed, Chartered Professional Engineer and registered RPEV in Victoria and RPEQ in Queensland. Today I'm going to talk about the technical aspects of a true example of footing design of the precast type so we can get to know what information we need to have, what standards we need to use, what sort of loading and load combination we need to take into consideration to conduct the footing design for industrial building. The example would be about the amine treater. Contents are structural characteristics and loading combinations. So first we need to talk about the geometrical characteristics of the structure that we are going to design the footing for and what sort of load combination we need to consider. Then we will move on earthquake design according to AS 1170.4. We're using a structural toolkit for the calculations and checking the stability of the footing. Then we will move on the design for the wind, and we're going to use a structural toolkit again. Then after getting the footing the dimension for the wind and earthquake, we need to do the analysis of the footing. In order to conduct the footing analysis to find out the internal reaction, including the shear forces and moment, we will using space gas. Then we will check the concrete shear capacity as per AS 3600 2018. Then we will design for the flexural reinforcement and shear connectors. Because this is a precast concrete footing, we need to use shear connector to connect different pieces of the footing. Part 1, structural characteristics and loading combinations. The first part is to calculate the earthquake forces. For the earthquake, we will using AS 1170.4, and for the concrete, we will using AS 3600. For this structure and the location that it is going to be built, the importance level is 2. The probability of accidents is 1 per 500 years. Probability factor Kp is 1. Soil class is B. Hazard factor Z is zero point 0.1. Spectral shape factor CH, which is dependent of the period of the structure is 3.5, and ductility and performance factor SP over MU is 0.38. As you can see here, by going through the standards, we can find out that the importance level is 2 because it is for buildings or structures not included in importance level 1 and 3 and 4. So what is important? 1, building or structure presenting a low degree of hazard to life and other property. And build 3 is buildings or structure that are designed to contain large number of people, which prone the people to danger. Might Failure might result in the life losses. And building for structure that are essential to post-disaster recovery, like emergency or hospitals, lie into the importance level 4. So for this structure, which is, treater, the importance level is 2. Annual probability of accidents is, as you can see here, for the importance level 2 is 1 per 500. And for the earthquake design category, as you can see here, mapped hazard KPZ for the soil class B, should be lower than 0.11. And for the location that we are going to build up the structure and the footing is designed for, the Z is zero point 0.1. And design base shear coefficients, the spectral shape factor for the concentrically braced steel frame. So this is the bracing system for the structure and light roof and concrete slab on ground with sheet cladding is 3.5, and ductility and performance factor SP over mu is 0.38. In order to calculate the base shear as per standard, we have this equation. V is the base shear, CHT1 is the spectral shape factor, Kp is the probability factor, Z is the hazard factor, Sp over mu is the ductility and performance factor, and Wt is the structural weight. Substituting the amount into this equation, we have the base shear as the 0.13 multiplied by the weight of the structure. Here is a schematic view of the mine 3-tour skid, and here we have the dimension of this structure. The length of the structure is 16.2 meter. The width is 4.03 meter, while the height is 4.1. And the structural weight is 29.615 ton. And the in terms of the kilonewton, it's going to be 296 kilonewton. It is the dry weight. And the also we have the operational weight. So load combination that we are using are the 1.2 G plus 1.2 Q, which is the 1.2 multiplied by the self weight of the structure and vertical operational load. The structural weight, including the dry weight and operational weight, can be obtained from the client. Combination 2 is G, gravitational load plus earthquake. So self-weight plus vertical operation load plus earthquake. And combination 3 is the 0.9 G plus W, zero point 0.9 self-weight, vertical operation load plus wind. Here is the geometrical configuration of the building that we are going to design the structure, the footing for. So as you can see here, the length is 16.2 meter, the width is 4.3, while the height is 4.1. Part 2, footing design, earthquake using the structural toolkit. We have considered 12 independent footing, 6 footing each side as shown in figure 3A, which we will see later. The design is done for the middle footing that takes the biggest portion of the load, figure 3B. We will talk about it later, and the footing is designed considering the 85% of the operational weight concentrated on the parts on which the containers are placed. Here you can see the configuration of the 12 independent footings. 1, 2, 3. Here 6 at each side and both sides. So as you can see here, this is the plan. We've got 12 footings. And these are the footing that we will design for as the critical footing, and we adopt the design for the rest of the structure. Here is the tributary area. It means we have the loading. We consider the loading here, then distribute over these footings. So in order to calculate the force from the earthquake, we already learned that the base shear is 0.13 multiplied by the weight of the structure. The total weight of the structure is 411.8 kilonewton. The tributary area is the width multiplied by the length of the tributary area, which result in this amount in millimeter. Footing design load is 0.85. We already considered that the 85% of the load would be at the location where the containers are placed. So 80.85 multiplied by the total weight is the 350 kilonewton is the load that we need to design the footing for. The load per tributary area is 350 over the area, which result in the pressure kilonewton per square millimeter. An area for mid footing is 3240 multiplied by the width, which is 4.3 meter, and result in this value. And load per two mid footings is the calculation of the load per area multiplied by the area, so it's 175 kilonewton. And load per footing, so we have two footings each side, so just divide by 2. This is the final load that we need to design the independent footing for. Load combination 1 is 1.2 multiplied by 87.5 kilonewton is 105 kilonewton. Combination 2, which is for the earthquake, is 11.38. The center of mass, we need to calculate the center of mass, is the height 4.1 over 2 plus 0.8, which is considered as the depth of the footing. So this 2.85 meter. This is the center of the mass. And the my, the moment in the y direction is 11.38 here. This is the base shear multiplied by center of the mass is 32.43 kilonewton meter. While for the base shear in the opposite direction, as per standard, we consider 10% of the uh, force applied in the main direction or primary direction. This is the secondary direction. So the amount of the load is 1.14 kilonewton, and the resulting moment is 1.14 multiplied by 285, which result in a 3.25 kilonewton meter. Footing dimension. In order to design the footing, we adopted the structural toolkit. It helps to define, or it helps to find the footing dimension. There is a weight criteria of 2.5 tons that is set for the lifting purposes. As we already mentioned, it's going to be precast concrete footing. So the pieces are prefabricated in the manufacturing area. When we manufacture them and let them to set, after the manufacture is completed, we need to carry them and we need to transport them to the construction location and then lift them and place in the location. So based on the requirement by client, we are limited to 2.5 tons for each pieces. Footing dimension, all WD, lengths, widths, and depths. We consider the 1.85 by 1.85 and the total depth of 750. So By substituting the amount into the structural toolkit, we can check the stability of the footing. Footing weight is the dimension multiplied by the uh, unit weight of the concrete, which is 25 kilonewton. The weight of the footing is 6.55 ton. As you can see here, this is greater than the criteria that we had, so we need to use the pedestal system by considering three segments through the footing depths. The dimension of the pedestal system is 1.85 by 250 millimeter. So the weight of each part is 2.18 tons. And because it is the lower than the criteria, so it is fine and we can go further for the design. Part 3 is the wind design of the footing. In order to conduct the wind design, we use AS 1170.2. We consider P equals to 1.22a. A is the area, projected area, which the load is applied to. For the wind analysis, the shipping or dry weight is considered. Because the lower weight, the higher probability of overturning or failure is. So we can, to be in a conservative side for the design, we consider the dry weight of the structure for the wind design, while for the earthquake design, we use the operational weight, which is greater. We already learned that the seismic forces or earthquake forces are dependent of the weight of the structure, so that the higher weight, the higher base shear is. So in order to be in a safe side, we consider the operational weight for the uh, seismic design. The footing design load is 0.85 by 296, which is the dry weight, which is 251.77 kilonewton. Load per tributary area is this amount, as you can see. The area for mid footing is the 3,240 by the width 4,300, which is this amount in square millimeter. Load per two mid footings is multiplication of the unit load by the area, which is 125.9 kilonewton. And because we have two footings, independent footings at its either side of the tributary area, we divide this load by two. So we need to design for this loading. The structure is not a complete box, as we could see in the typical demonstrator structure. 80% of the area is considered for the wind analysis. So AX here is point A multiplied by 3.24 multiplied by the heights. This is length and this is the height, which is 10.63 square meter. And the force we already learned is 1.22 multiplied by A, which is 13 kilonewton. So load per footing for two legs is 6.5 kilonewton. My, the moment in y direction or primary direction is Px, 6.5 kilonewton multiplied by 2.85, which is the height here, which is the center of the mass height, is 6.5 kilonewton multiplied by 285 is 18.53 kilonewton meter. In y direction, Again, we calculate the load. AY is point A. We already consider 80% of the area because it is an open area. And Fy based on the equation 1.22 multiplied by A is 17.2 kilonewton. So load per footings, we have 12 footing is 1.44 kilonewton. Mx in the along the length of the building is Py multiplied by 2.85, which results in 4.1 kilonewton meter. Structure toolkit is used to find the footing dimension, and as the wind load is much lower than the seismic force would be dominant. By the way, we also check here in structural toolkit the footing dimension 900 by 900 by 750, and we go for the footing analysis in space gas. As we already mentioned, for the design, we for the design of the footing and to find the footing dimension in terms of the stability, we resulted in the 1.5, 1.85 by 1.85 by 750 millimeter, which is the dimension required to withstand the seismic forces. The section is BD. B is the width and the 750 is the depth. Footing weight, we already have this weight, 64.17 kilonewton, and W is 6.54 tons. Load per footing for earthquake, we already calculated for the tributary area, which is 175 over 2, resulting in 87.5 kilonewton. The slab is two-way, so we need to again divide the force by 2, which results in the 43.7 kilonewton. Load per footing for wind, we have the 125.9 per over 2, which is 62.95 kilonewton. And the slab is two-way, so we divide it by 2 is 31.48 kilonewton. The load combination 1.2 G plus 1.2 Q. The combination 2 is G, which is a gravitational load or combination of the dead and live load plus earthquake, and for the combination 3.9 G plus W, which is the critical. Here is the modeling in space gas for load combination 1 and load combination 2 and load combination which we have the longitudinal and transverse. We have two model. We applied in both directions to get the reaction, including the moments and shear forces. And here is for the load combination 3. We just applied the forces that we already calculated and used in a structural toolkit. We also applied them on the footing here in space gas Y to check the strength of the footing. We already using we used the structural toolkit to check the stability and dimension of the footing. Now we need to check if the footing has adequate strength to withstand these loads or not. And here we have the typical footing reaction for the combination 1, and here is for the combination 2 in longitudinal direction, transverse direction, and here is for load combination 3. And the shear forces also could be found for the longitudinal transverse forces. And here is for the combination 2, and this is for the combination 3. And one important for the space gas modeling is to use the spring, because this is the footing, So we need to go through the geotechnical report and find out the soil bearing capacity to be able to define the spring stiffness so that we can model the structure soil reaction in a space gas and have a true representation of the soil, and we can rely on the results. And here is the shear check, the lengths, widths, and depths. Here is the footing dimension, and the concrete strength is 40 MPa, and concrete cover considered to be 50 mil, and we use N10 rebar as the mesh. The concrete capacity based on the AS36 shear capacity based on the AS 3600 2080 can be found by VU, VUC plus VUS. C is the shear capacity of the concrete section itself, and S is for steel. And here are the equations that we can use to check the shear capacity. And dV is the maximum of 0.72 D and 0.9 D. This is uh, given in the standard for the shear capacity if to refer to the shear capacity check. So you can find this equation in the standard A3600 2018. D equals 750 minus the cover minus the rebar, and minus 5 is the half of the rebar because we consider two mesh. And 0.72D, this is the effective depth, and this is 0.72D. D is the total depth, which is for 540 mil. So we use the 0.09D, which is the 616.5, which is greater than this 0.72D, and we use this one. dV is 616.5 millimeter. And we need to use these calculations to find out the epsilon and KDG. Here is m star BD2, BD square equals to phi of C, which is the concrete strength, Q1 minus Q7. Substituting the amount, we have the moment 50.3 multiplied by 10 in power of 6 over the structural width, footing width, which is 1850 millimeter, multiplied by the effective depth, effective depth, which is 682 square, equals zero point 0.6. This is the phi given in the standard, and 40 Q1 minus Q over 1.7. So from this equation, we can solve this equation for Q and find the Q. Then Q is ALCFI over BDFC. Substituting the Q here, we can find out the required steel for the section. Then we can substitute this amount into the equation for epsilon, and we can find epsilon. This is the strain. And KDG is equals 1, and KV can be obtained by substituting this amount into this equation. So the phi VUC is 426.59 kilonewton. How we can find it? By this equation. Then in order to find the flexural reinforcement, we have M star, which is ASTFID minus A over 2. This can be found by the stress block. and ALC is 184.75 square millimeter per meter. So we can use N10 at 300, which is spacing in both directions. In order to design the shear connectors, we can use V equals to the applied shear forces Q over IB. Q can be found by A multiplied by C. A is the cross-section area and C is the spacing between the bars. We have the area, we have the moment inertia in x direction. We have T, which is 250 millimeter. As you may already know, we consider the depth of the footing 750, but because of the weight limitation, we had to use three pieces. Each piece has a depth of 250 mil, and the width is 1,850, and the required based on our calculation, the amount of the available steel is 462,500 square millimeter, and C spacing, so QC can be found. We have the applied shear force, so we can find the V star as 274 1.43. And in order for the shear connector, we can use N16. We calculate the area of the each bar, 200 millimeter point 200.96 square millimeter. Phi V can be found by this equation, which is the shear capacity of each bar. And we have the applied shear force that we need to design for the vertical shear, and the shear force um, capacity of each rebar is 48, so the number of the required shear connectors is 6, so we have 12 in total for both x and y direction. So finally we use 12 shear connectors plus 4 uh, uh, down anchors, hold down anchors, in order to tie the pedestal to the bottom of the footing. And the shear connectors are distributed over the plan of the footing, as you can see here. We have 3 here, we have 3 here, and we have, so in total we have 12, and these are the hold down anchors. Here in this section you can see hold on anchors, then later can be connected to the pedestal. Thanks for your attention, and if you have any question, please don't hesitate to contact me on behzad.alb@gmail.com or behzad.bright.eng@gmail.com, or put your comment in the comment part of the YouTube channel, or just contact me on LinkedIn. Thank you so much, and we'll see you in the next tutorial. Bye everyone.